Hi guys, let's move on to EM wave in lossy media. So basically the lossy media we cover today is basically conductor, right? So conductor. So when wave, electromagnetic wave propagate along the conductor, right? Then uh, there will be loss, right? So there's electrons are colliding with the atom, so there will be conduction loss, so that the wave will decay, right? Decay means reduced, right? So that this kind of phenomenon will be explained in this lecture, and then this is very important kind of theory or some concept which will be used in microwave engineering. So so because for this case we consider the loss. So here, if you see in the Maxwell's equation, we have a j here, right? So we cannot remove this term, so we should kind of maintain this term. But for this case, we can remove to 0, right? So that is source free, so no charge, right? So the situation is that in the conductor we don't have any extra charge source, but we should maintain this conduction loss, right? So only difference is here, right? So if we use this equation, j omega epsilon e take j omega so that epsilon minus j sigma divided by omega, right? So we have this term. So previously low loss medium we had this, right? Simple, but it changed to this. This was a real value, and this is complex number. So we just take this as a epsilon c, right? So actually in this book, Pojar's book, they distinguish this epsilon actually. So as you understand, then this epsilon is just a real number, right? But in reality, we can also make this as a complex number itself. So what does it mean? Not just like a number, but if you understand the meaning is actually this is a real number. This is a lost term. So I explained that the origin of this permittivity is kind of polarization, right? In the dielectric medium, this plus minus dipole moment align, right? And then if electromagnetic wave change in time, this will change, right? Polarization plus minus, after some time this become minus plus, right? So this kind of change will make some loss, so then it will make some damping, right? So kind of loss. So this kind of dipole moment also have a loss when this is oscillating, right? Plus minus change in time. So we consider here as a loss, So we put this kind of term minus j epsilon with this notation. This is coming from damping of vibration or oscillation. Vibration of dipole moment, right? Due to dipole moment. So it's dielectric loss. So you can imagine that, right? So this kind of loss also possible, also exists in the real dielectric material, right? Glass, any real material. So in the book, they put it like this, right? So they distinguish, this is a dielectric loss, this is conduction loss, right? This is conduction loss. Conduction loss is coming from free electrons, when free electrons collide with atoms, right? So this one, complex permittivity can be represented like this, right? So there is here we have a very important parameter in microwave is loss tangent. So loss tangent, the definition is imaginary number of complex permittivity and real number of complex permittivity, right? This is definition. So imaginary means loss, right? So you can from this you can easily make like this, right? This is loss tangent, but in this book they distinguish this is coming from dielectric loss, this is coming from conduction loss. So in reality, this phenomenon kind of happens different case. What does it mean is, if we imagine conductor, right? Conductor, let's say copper is used for the wire, for the electric current. So this one has a 5.8 times 10 to the 7 Siemens per meter. So this copper is generally characterized by this conductivity, right? So for this case, this term is not used, right? And then for dielectric case, so dielectric case, most kind of commonly used dielectric in microwave engineering is PCB kind of dielectric. So if you see in your cell phone and the PCB inside, there's like some kind of line, and then there's some ground. This is PCB, and then in this this is signal line. Yeah, you will learn that later, but this is ground. So in between, right, in this conductor, this is also conductor. These two conductors should be separated by some material, right? Dielectric. So this dielectric is commonly used in microwave engineering. So this kind of dielectric has a loss tangent. So we characterize this kind of material, this dielectric material, with a loss tangent. So normally 0.004, something like this. So that this is very low number, right? So what I mean is, so this is some mathematics, right? So some definition, but in reality, we normally take loss tangent for conductor is, so loss tangent, we just make this name tangent loss for conductor, usually like this. For dielectric, because this damping from a dipole moment is dominant, we just call this, right? So this is very low, as I said, right? And this value, because this is very high, right? 10 to the 5.8 times 10 to the 7, this is very high, so this is high for the conductor, right? So if people ask what is loss tangent, you can say like this definition. Normally for the conductor, we use this term for the loss tangent. So let's move on to the wave equation using this this new equation. So for this case, so as I said, so this term is normally small for this small, so that we just assume that it's real, right? So basically this term is 0, right? So damping from dipole moment is 0, dipole moment oscillation is 0, so we just make this equation. Right, so using this equation, the previous lecture we got this, right? This is wave equation. So we just, this term is omega square root of mu and epsilon is beta, right? So beta square, this become beta square, and then so we calculate this one is one example of this electric field calculated like this, right? So this is a lossless case, right? Lossless case. So conductivity is 0. But for this case, so this become omega square epsilon and mu and epsilon c, complex number and 0. So this we just take this is gamma, right? So we put this omega square mu and epsilon c to minus gamma square, right? So this one, this the solution for this equation, one of the solution can be the difference is here, right? So difference, because this is a minus here instead of plus, so here we don't have j here, right? We just use minus gamma x and plus gamma x as a solution. So because gamma, so from here gamma can be j omega square root of mu c. So if you take j omega, so epsilon complex epsilon is e epsilon minus j sigma divided by omega, right? So if we plug here, So this is a previous beta we have. Only term we add is here, right? So this is a gamma. So we call this is gamma as a propagation constant. Propagation constant. And then this is complex number. We just put this as a alpha plus j beta. So this term is becoming similar, right? So if we put j here, the term will be similar. So if we plug this one gamma to here, right? So here, then ey j beta x plus this should be alpha x beta x, right? So this is a phasor form, right? This is complex number. So if you want to have a instantaneous form, if we want to see how this field change in time, we need to change this to we should just take a real number of this, right? So this is instantaneous form. So this become right. So this is only amplitude, right? Only real number. So it come out right as it is, but this has a cosine term in the real number. So we just only take cosine value. This is plus alpha x and then cosine omega t plus beta x, right? So this is an instantaneous form. So if you just take this form, right? So the difference is this term is only added, right? So this term was same as lossless case. So what does it mean by this? So if this, and then one thing you remember is this is a wave, EM wave propagate to along plus x direction, right? X direction. So if we this x, so wave is propagating this way, right? So we cosine, if we take t0, we normally have this term, right? But this is for lossless case, but this is alpha x, which means when x is 0 is 1, but it decreases, right? Something like this. So that this wave should be like this, right? So this wave representing this type of this pattern, right? So the difference is that as wave propagate to the positive direction, right? Wave amplitude of this electric field is decay. So we call decay or attenuate, kind of decrease, right? Electric field is decrease. So that this term, we call this is attenuation constant. Beta is same as phase constant, right? So phase, this is lambda, right? Lambda is 2 pi divided by beta, right? Beta. So So this phase constant is same as before, but the difference is electromagnetic wave decay as propagating to the positive direction. So if you see this one, right? So if you see this one, it looks kind of increasing, right? So in physically, right, if so we can understand electromagnetic wave propagate along the conductor because of uh, conductor loss, right? This wave amplitude becomes smaller, right? So from the loss, so we can understand like that. But this looks kind of increasing, but you should know that this wave is propagating to the minus x direction, right? So this is x, this is electric field, right? Amplitude. So e, this function, right? This function is increasing like this, right? This is 1, it is like this, right? But the thing is, this wave is propagating to the minus x direction, right? Propagation direction, beta, right? So that if wave is as wave propagate to the minus x direction, the field magnitude is decreases, right? So this is also represent attenuation, right? Because of direction of this wave is opposite, right? So normally for this attenuation constant and phase constant is important in conductor, right? So as I mentioned, so go back to this kind of dielectric constant for the dielectric used in this kind of circuit, right? In your cell phone's PCB, this is very low, so that the effect of this attenuation is very low. But in conductor, this attenuation becomes significant. So we consider when this is happening, right? So as I show you, conductivity is 5.8 times 10 to the 7, right, for the copper. So this is very high number. So if this sigma is way higher than omega times epsilon, this propagation constant can be changed into simpler way. So because this value is way higher than 1, we can just take this 1 out. So minus j and sigma omega epsilon, right? So if this j is go inside, then so it will be like this, right? So put j inside and then take care all the constants. Mu sigma square root of j is this, right? So we can make like this. So alpha and beta become same, right? Alpha and beta become, basically sigma is high, right? Alpha and beta is very high. So what does it mean? So basically beta is high means gamma sigma, this lambda becomes smaller, right? That is about phase constant. What about alpha? So the wave was represented like this, right? So if we define the distance, right? The distance, maybe let's say here is this is skin depth. So the depth, this is meter, right? The depth, that where the electric field, so this is a E0 plus, right? E0 plus divided by exponential, right? E, then we define the distance which provide this reduced electric field as skin depth, right? So if we plug skin depth here, so E0 plus divided by, right, multiply by epsilon to the minus 1, so the skin depth is 1 over alpha, right? So we just can put it like this. Alpha, we know the alpha, so this is skin depth. So this is meter, right? So skin depth means, right, some electromagnetic wave hits this conductor, right? So this alpha means this wave decay very fast, right? And then field confined in this surface, skin, right? Skin. And the other, this, let's say this is conductor, very thick conductor. Signal only exists in this skin depth, and then the other one is almost zero, right? So that's why we say skin depth, right? Because in conductor, skin of this conductor, most of electric field is confined. So one important thing is actually this skin depth is proportional to 1 over f, 1 over square root of f, right? So if you plug copper at 2.8 gigahertz, the skin depth is 1.23 micron. So you can simply plug a number, right? Then you will get this skin depth. So, and then in the first lecture, I said we try to use this kind of very high frequency, 28 gigahertz for the millimeter wave or 5G communication. What does it mean, right? The skin depths become 1.23 divided by square root of 10, right? Because the frequency increased 10 times. So this will be 1 over this skin depth. So one thing we can learn is as frequency goes up, right, skin depths become small, right? So that energy, electric field is confined in a small skin depth, right? I mean, so that is difference. So we will understand what does it mean by small skin depth in high frequency. So this is a skin depth. It's a very important concept in microwave. And then another parameter is intrinsic impedance, right? Intrinsic impedance. The ratio of electromagnetic wave, electric field and magnetic wave. So from this equation, so as we did before, so we can calculate H, right? So this one simply have one term. So if you plug EY, then so this come out minus, right? Gamma. This term is a plus gamma comes out, right? Because derivative along the x, j omega mu. Right? So if we compare this term, right? This term become plus, so that this is h, right? So if we compare E, h is propagating to the plus direction, right? 0 plus then 1 over, so basically right, plus like this, right? So that this intrinsic impedance become this way. So similar as lossless case, but this changed to the gamma. So this one simply can be converted to this, the equation with the complex permittivity. Simple as this, right? So for the for the general material, so we make this. So for this case also, if sigma is very higher than omega times epsilon, then so this term will be very high, right? Then number one, so that this intrinsic impedance, so just call this complex of intrinsic impedance is 1 over minus j sigma divided by omega e, right? Omega epsilon. So this is put it like this, and then j, right? J square root of j. This becomes 1 over j. So this is in if we make phase term, if you have some phase difference, this is 45 degree, right? This is j is 90 degree, 45 degree, right? So what does it mean is electric field and magnetic field has a 45 degree phase difference, right? In lossless case, there was no phase difference, right? No complex number of this intrinsic impedance. So lossless case, E and H are in phase, right? So no phase difference. But this conductor case, there is a 45 degree difference between electric field and magnetic field. And then if we make this as a complex number, then we can use this one, right? So this one become so mu pi f mu sigma and divide by sigma and then 1 plus j. So if you change this one, right? So what does it mean? This one is 1 over skin depth, right? So this become 1 plus j. So here sigma is a Siemens per meter, right? And then the skin depth is meter, right? So this become ohm. So this intrinsic impedance is ohm, right? The unit is ohm. So if you see this parameter, so using this combination, you can easily see that this become ohm, right? So this is same as the unit of this intrinsic impedance. So for this case, so let's finalize with this concept with surface resistance of conductor. So I will connect this skin depth to the loss in the conductor. So So let's say this is conductor, right? So and the electromagnetic wave is coming from this side, beta x, right, in air or vacuum. So this is a 0, x 0, and then z, right? So if electric field is hit this conductor, as I said, right, this electric field is decay very fast, right? So at some specific distance, skin depth, the electric field will be 1 over electric field divided by E, right? So electric field is decay very fast. We define as skin depth, right? And then here, when x is 0, electric field is E0, right? If we plug in this 0, then at the surface, x is 0, electric field is E0. So if we have a conductor of sigma of this conductor is this sigma, then J is sigma time electric field, right? 0 electric field at this surface. And then we define this as a W. W, and then there will be this surface, right? So this surface is defined by the area of W and skin depth, right? So if we want to make current, then we J times W and skin depth, right? So this is, and then if we take this as D, right, voltage will be ED. So E0 D. So voltage at the surface, right? So if we make this resistance V divided by I, then we can easily know that this becomes skin depth times sigma dW. So this is ohm. So as I mentioned, this is ohm. dW is a meter, so it will be gone. So this is ohm, right? So this is resistance. So when D and W is 1 meter, then R is become RS, surface resistance. So this is skin depth times sigma, and this is denominator, right? So 1 over this sigma and skin depth. So we call this is surface resistance. So as you see, right, as frequency goes up, right, this becomes smaller. As frequency goes up, this is getting smaller, right? Then RS become increase, right? So as this frequency goes up, skin depth reduced. That means surface resistance. So this conductor will have more surface resistance, right? So this surface resistance will be connected to the power loss of this medium here, so that that will be covered in the next session.